Self-attention is the mechanism that lets a transformer decide which other words matter for each word it's reading. In this topic, we'll open that black box with simple stories and build an intuitive feel for queries, keys, values, and attention weights. You've already seen why sequences matter, how earlier models struggled, and where transformers improved things. Now we'll zoom into their core, self-attention. Our goal is to build an intuitive sense for how it represents context, so you'll be ready to fine-tune real models later. Here's the core challenge. Language meaning is spread across the whole sentence, but older models like RNNs read one step at a time. Early words have to travel through many steps, and their influence fades as they go. Self-attention flips this. Every token can directly look at every other token at once, in parallel. The model learns which other tokens matter most and builds a richer context-aware representation for each word. In self-attention, every token plays three roles. Its query is the question it asks: what am I looking for in other tokens? Its key is like an index card: what information do I offer? Its value is the actual content to share. We learn separate query, key, and value vectors, so searching, matching, and sharing can specialize. Think of each token's query as a question you ask a library. All the keys are like index cards describing different books. The model compares your question to every card, measuring how similar they are. Some keys line up closely with the query, others barely match at all. What matters here isn't the exact numbers, but the ranking. Which tokens look most relevant for answering this token's question? Once we have similarity scores between the query and each key, the model has to turn them into a decision. How much should I care about each token? We run these scores through a softmax, which converts them into weights that all sum to 1. Large weights mean strong focus. Tiny weights mean almost ignore. Now we turn to the values. If queries and keys decide who to listen to, values are what's actually being said. Each token's value is a processed version of its embedding, tailored for what it can contribute. For a given token, its attention weights are applied across all these values, then averaged. The result is a new vector, a context-aware representation that blends information from the most relevant tokens. Self-attention's real power is that it rewrites each token's meaning using its neighbors. In the sentence, "He dropped the glass and it broke," the word "it" learns to focus most strongly on glass. So the new embedding for "it" now encodes the glass that just fell, not some generic object. Stacking layers on top of this lets the model build richer, more abstract relationships over time. You can also picture self-attention as a big grid of relationships between words. Each word in the sentence scans all the others and decides who matters most for me right now. Those decisions become attention weights. Strong links glow bright, weak links fade out. Patterns start to emerge, like pronouns locking onto the nouns they refer to, or verbs tying together subjects and objects. This grid is how the model builds rich context from simple pairwise connections. Self-attention doesn't rely on just one lens, it uses many. Each attention head has its own Q, K, and V, so it can specialize in a particular pattern. One head might track subject, verb agreement, another long-range links, another punctuation and phrasing. Then all these views are merged, giving each token a richer, more nuanced representation. With an RNN, each token depends on the previous one. Token 3 can't be processed until token 2 is done, and so on. In self-attention, every token is turned into Q, K, and V at the same time. One big matrix operation then captures all their interactions. GPUs and TPUs love this pattern, which is why transformers train so quickly and scale to huge models. RNNs and LSTMs read sequences one step at a time, carrying a small hidden state forward. That makes them slow, hard to parallelize, and prone to forgetting information that's many steps back. Self-attention takes a different route. Every token can directly look at every other token all at once. That gives it global context, strong support for long sequences, and a perfect match for modern parallel hardware. Self-attention isn't limited to words. It's about relationships between tokens of any kind. In images, tokens are patches, so the model can connect a tiny region to something far away in the scene. In audio or time series, tokens are time steps, letting it link events many seconds apart. In multimodal models, text tokens, image patches, and audio steps all attend to each other. The same queries, keys, and values work everywhere. Here's a quick mental checklist for self-attention. First, every token becomes an embedding, a vector of numbers. Next, each embedding is projected into three new vectors: query, key, and value. Then, each token's query is compared with every key, giving similarity scores that we normalize into attention weights. Finally, those weights mix the values into a new, context-aware representation for each token, repeated across heads and layers. Self-attention lets every token build meaning by looking at all the others. Queries, keys, and values define how tokens search, match, and share information, while attention weights capture who depends on whom. From here, we'll plug this into real workflows with Hugging Face, fine-tuning, and practical prompting.